This is lecture 3. We're going to continue from lecture 2, where we had discussed the equation for the geodesic and defined the Christoffel symbol. So just to very quickly review, we said that 2 points on a manifold that are separated by small differences in coordinates dx, the line element is then defined as this. G mu nu is what defines the local geometry of a manifold. Then we said, suppose there are 2 points which can be at a finite distance from each other. In that case, we said that to minimize the distance between them, we use Lagrange's equations, which I derive for you. And then we came to this equation d2 ds squared. So I called it, well, let me use the same notation as before. So x double dot rho plus gamma rho mu nu x mu dot x mu dot, where x mu dot means dx mu by ds, but it could also mean anything else. It could mean time, it could mean any parameter which increases as you go from A to B. And after some little effort, not much, we found that this was half G, let's call this phi. It doesn't matter what you call the indices, but you've got to be consistent. So okay, there was d something, dg something by dx plus dg something by dx minus dg something. And now let's fit in what the indices are. And here a little bit of memory helps, but also we remember that mu nu is this is symmetric under exchange of mu with nu, and there's one term here, mu nu, and then this rho has to be contracted. So one term we definitely know. The other one will be d mu, and then this has to be done with rho, and this will be nu. Now you flip nu and mu, so this will be nu rho. So this is how, at least I remember it. You know, if you have a few principles by which you can remember a formula, it's always useful to do that. What we did the last time was also, we said, let's take S1. In that case, there's only one coordinate, x1, which is theta, circle, and S1 is the curve x squared plus y squared equals r squared. And in that case, ds squared is equal to r squared d theta squared. Okay, and obviously there's only one metric quantity here, which is g theta theta, which is r squared. And then we said there's the metric with the indices up above, g theta theta, and what is that equal to? 1 over r squared. And so a circle is as simple as you can get. Okay, so then let's apply let's see what the Christoffel symbol is. Well, g theta theta is the only metric component, and it doesn't depend upon theta. So all of these are 0, which means that I have from, oh sorry, this is equal to 0. That's the equation. And so what does that say? So the geodesic equation is theta double dot is equal to 0. In other words, d2 theta by, let's say, ds squared. Let's choose, let's be now firm about it. We'll always take this to be the length along the curve, so the arc length. This thing is equal to 0, and any child knows how to solve this. Theta is equal to some constant times s plus some other constant c. And if you start by measuring distance from 0, let's say you're 0, at s equal to 0, theta is 0, then this obviously c, that means that c has to be 0. Okay, so geometrically what this corresponds to is that if you're on S1, then as you go from here to here, so theta increases from 0 up till here, then this length over here is omega s. Okay. Yeah. So this length from here to here is omega s. The further you travel, the greater the value of theta. So theta is proportional to s, which is a solution of this differential equation. We can't have it any simpler than this. Now let's go to something which is, Mike.
Sir, in any circle, if I move from point A to B, both s and theta are increases, right? Are increasing. So if in terms of affine parameter, either s is affine parameter or theta in this case.
S is the affine parameter. So I start from s equal to 0. Let me take this as the starting point and this as the ending point. So I am moving, as I move along, I'm traveling a bigger and bigger distance, and correspondingly theta is increasing in proportion. So S is the affine parameter. Yeah.
Sir, you have mentioned that the arc length is omega s. Shouldn't it be s only instead of omega s?
I mean, just any constant times this. You don't like omega? I'll put, what symbol do you like? What's your favorite symbol? Alpha? Okay. Then this becomes this. Because you see, this equation cannot determine the value of alpha. All I can say is that d theta by dt, d theta by ds is alpha, and then theta double dot is obviously equal to 0. So that's the solution of this equation.
Sir, it's fine, but I'm talking about the image you have drawn there.
Yeah.
At the circle, you mentioned that the arc length is alpha s, but alpha s is equal to theta. So shouldn't it be like arc length should be s when we multiply it with alpha and it becomes theta?
So arc length should be
s only.
Let's say that this, okay, so Okay, good. How much should this be? So if this is R, then how much is this length over here? R theta is equal to alpha S. So you could write this as theta is equal to alpha over R S.
So then S is not the R.
Well, if you want S to be the, okay, so right, okay, good. If S is the arc length, then S is equal to R theta. Yeah. So
Then alpha should be 1.
Yeah, sir, alpha S should be the arc length.
what?
Sir, alpha S should be the arc length.
Yeah. So look, S equals R theta, or theta, rather we should write it this way. Theta is equal to S over R. See, we have an equation over here, d2 theta by ds squared. So do you agree that theta equals S over R is the solution?
Yeah.
Okay, so actually, so alpha is 1 over R. You differentiate this, you get 1 over R. Differentiate it again, you get 0. Hence, the geodesic equation is satisfied. That's all we care. That's all that this is telling us. The geodesic equation has to be satisfied. So we got back what we knew. That theta is equal to, that S is equal to R theta. Okay. Now let's do something less trivial. And now let's move to S2. S2 is, of course, x squared plus y squared plus z squared equals r squared, r being the radius of the sphere which is fixed. And then we go to polar coordinates. We say x1 is equal to r sine theta cos phi. No, we say x is equal to this, y equals r sine theta sine phi, z equals r cos phi. Cos theta, sorry. Cos theta. And then we write ds squared equals dx squared plus so then and then that works out to be, we did this the last time, so I'm not going to repeat this, r squared into d theta squared plus r squared plus sine squared theta d phi squared, from which we get g theta equals r squared, g phi equals r squared sine squared theta, and g theta phi equals g phi theta equals 0. And of course, this is also true. Okay, so all the metric components are there, both the lower indices and the upper indices, and now it's the boring task of putting all these in here and getting the components. How many will there be? Quite a few. But only 2 of them are going to be non-zero. Okay, now when you, by the way, we said that for a general tensor of this type, there will be n squared n plus 1 over 2 components. Huh? No, I said, anytime I say the word tensor, please excuse me, I have not talked about tensors. In fact, I will be doing that. I promise you, we will talk about vectors and tensors and talk about covariant and contravariant tensors. So you'll get a lot of dose of terminology today. But you see how many there are. Let's take 4 dimensions. We live in 4 dimensions. So this is 4 times 4 into 5 over 2, which is so that's 40. Quite a lot of components. And so we don't want to go to 4 dimensions right now. We want to stick to 2 dimensions. And then you can ask Mathematica to calculate in 4 dimensions, in however many dimensions. And actually, you do need these, let's say, when you are calculating the collision of 2 black holes. You need to actually calculate all the Christoffel symbols. But let's leave that for later. Okay, so look at this. So this is, let's take, so the 2 the 2 components that will be non-zero will be I calculated this yesterday, minus sine theta cos theta, and there will be phi theta phi, and that's because it's symmetric. That's also the same as this, and this will be cot theta, and all the other 0. All others 0. So let's say gamma theta theta, gamma theta theta phi equals all the others will be 0. No, phi theta, phi theta. Yeah. Theta phi is the same as phi theta, but all the others are 0. So let's see if we can spot this easily. why do you think gamma theta 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 would be 0? Let's think of that over here. So sigma is theta, rho has to be theta, so rho has to be theta, so mu has to be theta. So this is g theta theta divided by this being theta. But there's no theta dependence anywhere in the metric. No, there is over here, but g theta theta is not. G theta theta is independent of theta. And so this term is 0. For the same reason this is 0. This would be g theta theta. Again, that's independent of phi or theta. And so that's why this one is 0. And you can check all the others. That will also. So, you know, this is just nasty checking, algebra. Okay, but let's see now what these do when they're put in over here. Well, they have been already. Let's see what they do when they're put in over here. Okay, so now let's remember that x1 is theta, x2 is phi. And so the first equation here, we put rho equal to 1, which means that this is theta double dot. Yeah. So the first equation is this, theta double dot plus. And now let's put gamma theta mu and nu. There's, if you put theta over here, then looking over here, there's the only possibility is that this index is phi and this index is phi. So then phi, and then let's, so what will we have over here? Phi dot equals 0. Very good. So then we have theta double dot, and this is minus sine theta cos theta phi dot squared. So that's the first equation that comes out of this. And right. Let's look at the second equation. So this is our first equation. Second equation will be phi double dot. And now, so now this over here is phi. So sigma is 2 or phi. And if it's phi, then this can be theta and this can be phi, and the other way around. And so just put these in here, and we will get phi double dot plus 2 cot theta d theta by ds d phi by ds. So this is the second equation. Okay, these are not simple, very simple equations. In the differential equation lectures, you have been hearing about typologies of different differential equations. So what would you call these? Are these linear equations? Are they, what are they? What degree are they? They are definitely nonlinear because look, here you have the square of the dependent variable, and here you have also order 2. There's d theta, so there's theta dot and there's phi dot, and it doesn't look simple at all. What should we do? Okay, so let's differential equations is always like solving differential equations like magic. You always have to invent some trick. There are principles, but the principles are for linear differential equations where you can use superposition, and if they're constant coefficients, then solutions are exponentials. If they are not constant coefficients, then you use variation of parameters. You play games that way. So now we will have to play games here. I look at this, and what do I have over here? Phi double dot is d2 phi with ds squared, and this is equal to now minus 2 cot theta d theta by ds and d phi by ds. Okay, so I'm going to do something which nobody can object to, and which is I'm going to divide. I'm going to bring this down. And that makes this minus 2 cot theta d theta by ds. But what was the logic of my bringing this down over here? Can anyone see this? Huh? Yeah? Why did I divide?
Sir, to reduce the order of equation.
Yeah, well, maybe you're right. I don't know. But there's some logic to it. Okay, so suppose I have this dy by dx equals y. And I bring y down over here. What does that immediately tell you? Yeah, why did I, in this case, why did I do this? Okay, because I recognize that this is the same as d of log of y is equal to dy. Because when you differentiate log of y, you get 1 over y. So I'm going to use the same logic here. I'm going to say that this is d by ds of log of d phi by ds. Because if I differentiate this, then I will get 1 over d phi by ds in the denominator, and then I have to take the derivative of this by the chain rule, that's d2 phi ds squared. And on the other side, these won't be very useful unless I can get this as a derivative. And can anyone tell me why? Can I put something over here so that if I differentiate? Sorry, I missed out the theta. Yeah. Without that, it doesn't even make sense. Yeah. Okay, so can I put d by ds of something over here? Yeah? Okay. Almost true. Okay, so log of sine theta with minus 2 as the coefficient. Is this true? Because if you differentiate log of sine theta, you get 1 over sine theta, and differentiate sine theta, you get cos theta. So this is cot theta. So this is exactly that. Now, if that is true, then what does that say? That says that, so in fact, we can even do this, d by ds log of d phi by ds plus plus 2. In fact, let's do it this way, plus log of no, see, if I take here 2 log of sine theta is the same as log of sine squared theta. So that way I can get rid of the 2 equals 0. And then this thing over here, log A plus log B is equal to log AB. So d phi by ds sine squared theta. That's equal to 0. Okay, if d by ds of something is equal to 0, then what is that something equal to? A constant. Beautiful. So that says log of d phi by ds sine squared theta is equal to a constant. I don't care what you call the constant, call it anything. And now d phi by ds is equal to, let's call that constant L. L over and there's no other constant because when we solve this, there is only one constant. So beautiful, beautiful. Okay. Log. So d phi by ds sine squared theta log of this is equal to a constant, okay. I'm sorry, I skipped a step. That was log of this. So now that means this is e to the constant. And now e to the constant I will call L. And that says, gives me exactly what I had before. But that's fine. So now this holds for every value of theta. I didn't say what theta was, so, but it will hold for every value of theta. That's one equation. Now let's look at the other equation, which is this. Theta double dot is equal to that. And this is a nasty equation. Okay, what I can do is this is the same as phi dot, right? I can put it in here. So I have d2 theta ds squared minus sine theta cos theta phi dot squared, square of this. So L squared over sine to the power 4 theta. And one power goes and this becomes 3. And so this is equal to 0, and my equation then becomes d2 theta by ds squared equals L squared is cos theta over sine cube theta L squared. And that is a nasty equation, very nasty equation. Still you can solve it because but I don't want to solve it. I am going to say that look, this holds for every value of theta. And I can choose my coordinates in any way I want. So I will go from point A to point B, where I'll choose theta equal to pi by 2. Let's see if that is a solution. Let's see if theta equals pi by 2 is a solution. Okay. If theta is equal to pi by 2, then d2 theta by ds squared is equal to 0. Which means that if I start off with 0 velocity, so ds by dt is d theta by ds is equal to 0, then d2s, then d2 theta by ds squared, the second derivative will be equal to 0, which means it's not going to change its value of theta, and hence theta equals pi by 2 is a solution of this equation. Do you agree? If you start at theta equal to pi by 2 at s equal to 0, then it's always going to remain at pi by 2. Then in that case, d phi by ds will be a constant. So again, to underline, is a solution of the above, of this. Are you happy with this? Not happy. Then let me try and make you happy. Yes, You tell me your unhappiness. Yes. No, इनको दो. इन्होंने सर हिलाया था. Yes.
Sir, it seems very trivial to me.
Yes.
I mean, if a system is already at rest, then how are we going to study the phenomena we are trying to? I mean,
Yes.
it is already the solution, right? We did nothing.
We did nothing. Absolutely correct. So you agree that with theta equals pi by 2, theta dot is equal to 0. Theta double dot is equal to 0. And now take further derivatives of this. Take d2 theta by ds cubed. Differentiate this. You'll get theta dots over here. But those theta dots are also 0. So if you start with this, then you will never move off it. Now, as I said, I don't want to study this equation in its full generality because this is not an equation which makes anyone's heart glad. You're not happy to see this. It's a stupid nonlinear equation. But I have found a solution. So if you're now a bit happier, let's go.
So you said that that equation holds for every theta. So
Yeah.
what about theta equals to 0 or 2 pi?
Theta equals 2 pi would not work. Theta equals 0 would not work. In that case, I would have to solve the full equation. I'm only making the claim that theta equals pi by 2 is a stationary point of this equation. So you put it over there at theta equal to pi by 2, and then nothing will happen. If you are happy with that, then we can move on, but yeah.
सर लेकिन ये कि ऑब्वियस बात नहीं है, स्फीयर के टॉप पे कोई चीज़ रखेंगे वो हिलेगी ही नहीं. ये तो आप बगैर इतनी मैथ के बगैर भी बता सकते हैं कि ऊपर ये चीज़ रखें.
Well, look, you are thinking of a symmetry argument, and you are very correct to think of that. But first, let's ask what theta equals pi by 2 means geometrically. So this is the equator. There's a point on the sphere. Its coordinates are theta and phi. We're taking a fixed radius, so that's fine. And this theta is measured with respect to, so this is theta. Theta equals pi by 2 means that we are on the equator. Theta equals 0 means we are here. And you say that if I take any value other than that, it won't work. I don't want to solve this in its complete generality. I just need to solve it for theta on the equator. On the equator, this is what it is. Are you happy or not happy yet? Okay, good. If you, or at least pretend to be happy. Yes. This is not on.
Theta equal to 0, if you look at the right hand side of the equation, that would give a 0 in the denominator.
Absolutely. Yes. And theta equals pi by 2 will give you 1.
1.
Yeah.
And theta equal to pi will also give you 0.
Yes. And this, so theta equals 0 is this pole. Theta equals pi is the
South pole.
south pole. And let's do a better job over here. Yeah. So theta equals pi by 2 is the equator.
Yes, but this equation, then you have something infinite on the right hand side at these 2 points.
Oh yeah, oh yeah.
So what does that mean?
That means that you will have a singularity in theta as a function of s. So look, we can, if we really want to, solve this equation, but we don't need it. All I'm asking you to believe is that this is a solution, and I'm willing to defend myself on that.
So you
Ah.
It's the equation says that it's second derivative that's equal to 0 if you
Yeah.
put theta is equal to pi
Yeah.
by 2.
Yeah.
But you
This-
can integrate that and you can get theta as a linear curve as a function of s. So
Yeah.
I think this equation is not saying it's a stationary point, no?
Okay, so I'm saying if the initial value is this, theta is this, then theta dot is this, d theta by ds is 0.
Why
Okay.
would that be 0? I mean, you integrate
Initial
that.
conditions, initial conditions.
Oh, okay. So initially you started. Okay.
Initially, I start with 0 velocity.
Okay. So these are two conditions that would fix that.
So
okay.
here's, let me put it this way.
Yeah.
I have a car which is at rest, which is at a certain position and is at rest.
Okay.
Its acceleration is 0.
Okay.
The rate of change of its acceleration is 0, and the rate of change of that is also 0, and all the derivatives are 0. Therefore, I say the car will not move.
Okay. So that means if you start by moving along the equator, you would stay on the equator.
Yeah.
So you would.
Yeah.
Okay.
Yeah.
Thanks.
Yeah. There's, yes.
Sir, I think we still have the 5 degree of freedom to worry about. Theta is
I
just
am going
fixing.
to
Yes.
be very worried about it. Yes, I will.
So
tell you.
theta is just fixing where we are on the equator, and
Exactly.
then we'll see
exactly.
how we'll.
Exactly. Okay. So, anything else? Right. So,
Sir, but like in my head, this is only for when theta is equal to pi by 2.
Yeah.
But for other values of theta, what do we do?
then we solve this. Then we solve this.
Acha, okay.
Then be prepared for ugliness. I am making a very small claim that this solves this, subject to the condition that theta dot is equal to 0 at s equal to 0. All right, so now we worry about the other equation, and what do we get over there? d phi by ds is equal to L, because theta is equal to pi by 2, sine squared pi by 2 is 1. If this is true, then any child can integrate it. What's the answer? And if we say that at s equal to 0, phi is 0, then this constant over here is also 0. All right, so that says that as you move along the geodesic, the angle increases linearly. So as you go around, so this much is s, then phi will be r times s, L times s. And how much is the actual distance? Like in the case of S1 we had done, r times so S was equal to, the arc length is and so this L is 1 over R. So we have a solution to the geodesic equation. It's a big deal. I mean, look at the Riemann, the Christoffel symbol. We took that and we calculated all the components, then we put it into the geodesic equation and we got this. And it says that if on a sphere you want to go from here to another point on the sphere, you better follow the great circle. And let me make this a little clearer. So and I've given this as a problem in lecture 2, which I've added a problem to lecture 2, and the problem is the following. So this is our sphere. The equator is over here. I want to go from this point to, let's say, this point. So the same value of theta, so you see theta has a fixed value. I want to go from here to here. What is the path that will be shortest between them? So imagine that you are an airline pilot, okay? And one city is here, another city is there. They are both at the same latitude? Yeah. Latitude, yeah. They are the same latitude. How should he fly so as to get there in the minimum possible time, which means minimum possible fuel, which means minimum possible distance or cost? They're all the same in this case. So should he then fly along the latitude? Should he? He will get fired from his company because he has traveled too big a distance. And this is the problem that I've given you, and you will work it out explicitly. No, he has to travel along this path, and this path follows the curvature of the earth. So so there's always a great circle that goes through any 2 points. He has to travel on that. And so knowing the Christoffel symbol, so knowing what geodesics are from the course that the pilot took on differential geometry when he was in school, he will then keep his job. Okay, good. Now there is a lot of this nonsense we had to go through calculating the Christoffel symbols, which I hate. I always like to start from the basics. The basics in this case are Lagrange's equation. We used Lagrange's equations to get the equation of the geodesic, but why don't I look at the fact that my ds squared was this. And the thing that I was doing was actually this. Which is what? Do you remember all the G mu news and, sorry, this goes up. Can you write this for me? What is it? So it has to be diagonal, right? So it is G theta dot squared plus G phi dot squared. And what is that equal to? G theta was r squared. So r squared theta dot squared. And what was this equal to? Okay, so we had good. What was Lagrange's equation? There'll obviously be two of them. So one will be this. And the other one will be with theta. So there'll be theta dot and there'll be theta over here. All right, ladies and gentlemen, tell me, what is dl by d phi? 0. If something is 0, it makes our heart happy. So that says d by ds of dl by d phi dot. Look over here, dl by d phi dot is what? 2r squared phi dot equal to let's see. Sorry, dl by d phi dot. So didn't I get 2 from there? Because I differentiated this, so that's where I got the 2 from. But since this is equal to 0, it doesn't even matter whether you have the 2 over there or not. And what is this? This says that this thing is equal to a constant, which means that r squared sine squared theta d phi by ds is equal to some constant. Exactly the same. You see? So, why spend so much energy in doing the first route? Because I just wanted to show you both ways. One is the way in which you don't do any thinking, you just calculate. But here you do a little bit of thinking, because here you say, aha, this Lagrangian does not depend upon phi. So phi is what is called in, what's it called? A cyclic coordinate, yeah. So that's using that. All right, so look, I'm going to leave now the technical matter of calculating these quantities and we'll use the Christoffel symbol again and again when we discuss curvature. But now I want to come to something that is more basic and something that you have been waiting for very eagerly, and that is to learn about vectors and tangent spaces. Yeah. या थोड़ा आगे आके बैठ जाओ ना तो क्या ही कि इन लोगों से नाराजगी है कुछ नहीं ठीक
सर सो हमने वहाँ डी फाइव बाई डी एस में एल को हम लोगों ने 1/r भी कहा था ना बेसिकली तो यहाँ हमारा एल 1/r स्क्वायर क्यों बन गया वहाँ r स्क्वायर
any constant is okay with me all the constant will be fixed by whatever physical constraint there is, but in terms of solving the geodesic equation, what I've shown you is that phi proportional to s is what solves the equation. Right. So now we'll talk about tangent spaces, vectors, and one forms. These are also called known as covariant vectors. Or covectors. But here is the idea. We have some manifold, and we have a point on that manifold, and maybe I should try to make it look a little more three-dimensional. So imagine that you're looking at this from the side. Well, here is the point P. And locally it is flat. So we live on the surface of the earth. This little stage over here can be considered a flat surface with zero curvature, and because this is two-dimensional, see, I can move this way, I can move this way, I cannot move up, I cannot move down. So there will be two basis vectors, and E mu basis vectors in the two-dimensional, n is 2, let's say, n-dimensional tangent space, which is denoted by tangent at the point P of the manifold M, TPM. So I am on this little patch over here. A similar patch in San Francisco, which is on the other side, would be pointing in the other direction. This one is pointing out of the earth. Over there, it will also be pointing out of the earth, but it will be opposite. Yeah. Okay. So this is very, very local. So this is a local, so in the language of mathematics, this is a local patch which is isomorphic to R2 or to Rn in general. Okay. So a general vector, V mu, can be written as the components V mu, E mu hat. Yeah.
If the manifold is locally flat, then the tangent space won't it also be flat? So why do we need to define it in the first place?
Because
why can't you define the basis vectors on the manifold itself?
Good question. When I go to another patch which is a little further away, my basis vectors will be pointing in another direction. Because unless, of course, the earth is flat. We know it isn't, although for a long time we thought it was. But absolutely, this is on the, so this is why you say it is at a point. At point P on the manifold M. You go to another point and you will have different basis vectors. Go to yet another and you will have other basis vectors. And so these are basis vectors only and only at the point P. And that means you can write any vector as this. Okay, fine, no problem. But see, I'm calling this the x direction, this the y direction, and who said that I always have to use
Okay, so sir, you're saying that at this point you will have these basis vectors, and on another point you'll have different basis vectors, right? But why can't we just use these vectors to also like describe those points?
Because because those vectors will be pointing in some other direction. So let's take a sphere. I am at this point. There's a patch over here. And I have vectors that point here and here. At another place, so this is point P, I go to another place on the sphere and they'll be pointing elsewhere. So the basis vectors, as we go from point P to point Q on the manifold, we always have to stay on the manifold. You can't get off the manifold. Those basis vectors will be something else. Yeah. Or just to make this even clearer, take a circle. Okay. This is the tangent vector. This is a tangent space of dimension 1. This is the basis vector here. This is a different point on the manifold, and the tangent vector is pointing in a different direction. So there is, what does this vector have to do with this vector? They're different vectors. Yeah.
Sir, but like using your example for the circle, I agree that they're both pointing in different directions, but aren't we using this? Don't we use the same unit vector? Like वहाँ पे भी theta hat है, यहाँ पे भी theta hat ही होगी. Yes, the direction is different, similar to the sphere. Your theta hat, phi hat, and r hat are still like still the same along.
Good, but that point is then it's in the direction of increasing theta. That's what you're saying. But you can see that this vector is physically not the same as this. Okay, so now move away from.
Sir, so can we say that we are actually transforming our reference frame?
I don't know what to say about that. All I'm making the claim, you can give whatever words you like, but what I'm saying is there is a tangent plane at P, there is a different tangent plane at Q. If P and Q are the same, then the tangent planes are the same. But even if they are slightly separated, those vectors are not going to be the same.
Right.
So at every point on the manifold, you will have a plane,
Right.
a tangent plane.
Right.
And don't think of this as one-dimensional or two-dimensional only. When we go to n dimensions,
Right.
then it can be very different.
Right.
Right?
Okay, thank you.
Sir, when we are considering these tangents at the point P of a manifold, so do these tangents have to lie on the manifold or they can be away from the manifold?
Okay. You can see that if you follow the vector, they will go off the manifold. Like over here. Here is the vector.
Oh.
At the point P, it's going off the manifold. So only in a very tiny patch are you defining these vectors.
So
at the next point or a little bit away, it'll go either below or above.
Sir, but my question is, does this vector has to lie on the manifold or not on the manifold?
The tangent plane does not lie.
Vector, just a single vector in manifold.
Just one point of it lies on the manifold. That's the point P.
That's the only point, sir?
That's the only point.
Okay.
Unless, of course, if it's a flat space, then it's okay. Then nothing is changing. Yeah.
Oh.
Now let's think of the following. Here is a physical point P, a point P that actually exists. I can give this coordinates. I have given it coordinates. I've called them x1, x2, xn, xn. So these could be Cartesian coordinates, for example, but then we have seen we can give this, we can give a different set of coordinates to the same point. Let's call them x1 prime, x2 prime, xn prime.
Sir, a question?
Just absorb this first. Same point P, but different coordinates. And you have now plenty of, you at least you have one example in mind, polar coordinates. So you could call this x, y, z, x, y, with z being fixed because x squared plus y squared plus z squared equals r squared. So x, y, and here theta phi. Same number of coordinates here as here. Yeah.
Sir, question ये है कि you're saying कि जो tangent होता है in this surface only intersects the manifold at one point P, right?
Yeah.
And you're also saying that in a flat surface it doesn't matter because it doesn't really change, the curvature doesn't change, like stays
Yeah.
the same.
Yeah.
So does that mean that the manifold is not actually like flat though, because it's changing, right?
If it is a non-flat manifold, then the tangent plane will touch the manifold at only one point.
So, but manifold itself is considered a flat surface, right? So, shouldn't
Yeah.
the tangent like intersect the whole thing? Locally flat, yes.
Yeah. Yeah.
Yeah, locally flat. So, shouldn't the tangent intersect that whole thing that's considered locally flat there?
If we live in a flat world, then everything is okay. But we don't. Okay. So, the point is that we have these two different set of coordinates, and we could say that x1 prime and is so we could say that x prime mu actually depends upon x. So the primed coordinates and the unprimed coordinates, well, if you, for each x, so each set x over here, let's say theta phi, there'll be a certain value here. Okay. Now, so let's take dx prime mu. So I'm now considering the distance between 2 points which are very close, and this is going to be related to two slightly separated points which are without the primes. And how do we do this? Well, we use the chain rule. That says that any change over here results in a change over here, and of course that's so. For example, if I have x equals sine theta sine cos phi, y equals sine theta sine phi. Well, what is dx? Dx is, you see how theta, you see how this changes with respect to x, dx, and how, sorry, it's, yeah. And then how sine phi sorry, this has to be yeah. So d phi. How much it changes when you change theta, how much it changes when you change phi, and that's what this is telling you. Huh?
d sine phi by d phi and then sine theta.
Sine theta, yeah. Yeah. So just it is just the chain rule over here. Okay. Now this leads me to now tell you more about the basis vectors. And let's see, how should we define these basis vectors? Well, if I am going in the x direction, that means Ex should point in the direction where something is changing fast with respect to x. If it's the y, z, then something that is changing fast there. And in modern differential geometry, we take this as the definition of the basis vector, E mu. Now you'll say, but this doesn't, oh, I'm putting a differential operator over there. This is so unconventional, you haven't seen this before. But it sort of makes sense, and it'll make more sense as we go along, that if you're putting mu equal to 1, then this is the rate of change in the one direction, etc. Okay, now why is, and this is, remember, we are only talking about the tangent space, we are talking about the point P. What if at the point P we had chosen a different set of basis vector, E mu prime, and these are what we, so if these are basis vectors, what have you learned, what should we call these? Absolutely. Components of the vector. In the basis, in the E mu basis. Okay? Now, actually, you know, a vector is a vector. It doesn't matter how you describe it. I think of a vector always as something here. And okay, one of you might say that this has got components 1 and 2. Somebody sitting to the left or the right will give it different components because his reference frame is different. So let's see. What if I take different components? What this will do. Well, this is V mu prime, and this E mu prime is now going to be written no, V mu prime. But before this, let's first see how E mu prime relates to E mu. Okay, so E mu prime is d by dx mu. And when we change coordinates from, sorry, x prime, when we change coordinates from x prime to x, then this becomes with the sum over nu. Now this is taking a set of, this is making a linear combination of these, oh sorry, this, yeah. Yeah. V mu prime, on the other hand, so in the unprimed coordinates, V rho are the components, and those components now, I could have called this mu, but then I could have called this nu, but then we would be repeating indices, so why not call it this? Now I'm going to take this thing, E mu prime, V prime mu, and I'll plug this in over here. So this is, or let me write this this way. Okay, it's all right. So V prime mu I'm writing as this. V rho, and E mu prime I'm writing as this dx mu you know, we always like to abbreviate things, so this is called d nu. So all right, now this I'll take over here, and can you tell me what this is? Summed on mu, exactly, this is the Kronecker delta. So then nu has to equal to rho. Very good. which means that E mu prime, hence E mu prime V mu prime is equal to and since that change of coordinates did not make any difference, that says that they're both describing exactly the same vector. You can write this boldface, or you can write this with a little arrow at the top. But this is what we were discussing earlier, that how you describe a vector does not depend upon which coordinate system you are using. I have gone from Cartesian to polar, or I could have made some very complicated thing. I could have used coordinates that are highly twisted or whatever, but every point over here can be described equally well in the xy or the x prime y prime coordinates. And so this is really the modern way in which you look at vectors. There is a word for lower indices. So these are the basis vectors for a covariant vector, and this contravariant. Mike, please. Yeah, we are almost out of time. We are out of time, but yeah.
सर ये जो सारा वेक्टर है वी इस जिसमें बेसिस है और कंपोनेंट है, तो इन सारों को कंबाइनली कंट्रावेरिएंट वेक्टर नहीं कहते, क्योंकि बेसिस जो है वो कंपोनेंट के अपोजिट ट्रांसफॉर्म होते हैं.
Yeah, so you're correct that this over here is a covariant.
Contravariant.
Covariant.
सर कंट्रावेरिएंट क्योंकि बेसिस जो है वो कंपोनेंट के अपोजिट ट्रांसफॉर्म होते हैं.
So see, this is a this lives in the tangent space. It's actually, I'll say just this. This is a vector. The vector lives only in the tangent space. I'll explain this more next time, but anything which has got lower indices, so components which are like this will transform contravariantly, this will transform covariantly.
जब हम वन फॉर्म या टू फॉर्म की बात करते हैं तो उसको हम कोवेक्टर नाम दिया, मतलब वो कोवेरिएंटली ट्रांसफॉर्म होता है. उसमें जिस तरह हम जिस तरह बेसिस वेक्टर ट्रांसफॉर्म होते हैं तो सेम उसी तरह कंपोनेंट भी ट्रांसफॉर्म होते हैं, तो उसको कोवेरिएंट कहते हैं. और इसको कंट्रा नहीं कहते क्योंकि ये अपोजिटली ट्रांसफॉर्म होते हैं, तो इन सारों को कंबाइनली एक ये जो वेक्टर स्पेस में रहता है टेंजेंट स्पेस में, इसको कंट्रावेरिएंट कहे.
Okay, I will clarify, make this all clear the next time. We are out of time. But the important point is that we have looked at vectors only in the tangent plane today. And they are described by these bases. They are linear combinations of these basis vectors, which are d mu. Good. So more next time on vectors and tensors.